Good morning, sir.
All right. Maybe this is our last lesson. I will see if I'll try to finish the chapter. And just for, new chapter, I don't want to start this. And we will see. That much is enough for this semester. Okay. And I hope I could teach more and we could meet in the classroom. That is what it is because of the situation. As you know, every part of the world, actually everything actually turned into online. It's fine, and I hope at least you get some idea about the differential equations and about the methods, techniques, and as I always tell you from the beginning, in the future, if you're going to take a differential course again, or after all, who knows what happens tomorrow, if you, for example, study for your master's degree or PhD, and you will see that if you do anything related to engineering, again, you will actually meet this, concepts again. At that time, I hope you'll have some foundation so that you can just do some revision and help you to understand more, okay? And about the differential equations, as you know, it is very important for all engineering students, like fluid dynamics, also electric engineering, almost every engineering, chemical engineering, fluid mechanics, fluid dynamics, they all use differential equations a lot. Anyway, so that is our last lesson. If I cannot finish tomorrow, we will have a short session about final exam. As we talked yesterday, it's gonna be online. That is, actually I got permission, but not everybody is Phnom Penh. That is another problem. Chat, what is it saying? So will this section be recorded? Yes, of course. Now I'm recording, right? Yes. Will this session be recorded? I'm recording. Why he's asking like this? I don't know. Sereput, are you there?
Yes, sir, I'm here, sir.
Yes, Sereput, now I'm recording, right?
Oh yeah, I can see it now. I joined by phone, so I did not see that button. Yeah, I see it now, sir. Thank you.
Yeah, it is recording. Also, second session will be recorded and I'll share with you. Okay. So what we did last time, if you remember, we were talking about operational properties, number 2. And number 1 is, what is it? Translation on the s-axis, right? If you remember this, translation on the t-axis, that is what we did the last week. So now we are going to talk about operational properties number 2, derivatives of a transform. We already actually studied this. Now today we are going to talk about 2 different things. Number 1 is transforms of integrals, and second one is transforms of a periodic function. The Dirac delta function, also it is a very useful function, but I'm going to skip this. It's a kind of independent topic. You can learn this yourself. Systems of linear differential equations, and also the idea is the same. Maybe I will show you one example. And in chapter 3, we already studied how to solve this. But here, how can we solve this using Laplace transform? That's the only difference. Again, because systems of linear differential equations, we're talking about a bunch of equations, right? Linear equations, maybe equation 1, equation 2, equation 3. So you're just taking Laplace transforms of each function. And after that, you will have a system of equations in that f of s, or y of s, or capital X of s. And after that, using this system, you need to find that f of s, or that Laplace transform, and everything is the same. It's like solving linear equation and solving a system of linear equations. You know the idea, that because usually the idea of systems of equations is the same, either elimination or substitution method. Okay, so last time what we did here, we got this formula, right? Derivatives of a transform, Laplace transform of t to the power n times f of t is just equal to -1 to the power m, and derivative of s is f with respect to s, right? We're just differentiating this Laplace transform of f. So if this thing is given, right, and this our function is multiplied by 2 to the power n, and this is how we calculate. And also we have proved this already, and we did a few examples. That is example 1. I'm going to use this example soon again. All right. That is another example, initial value problem, okay? Mihoz darsam abdush ke halora gaplashelik. Transforms of integrals. All right, that's the last example. We are going to use this thing again. Now we are going to talk about transforms of integral. Okay, now we are going to be familiar or introduced to one special, product. Okay, that is called convolution of two functions, actually f and g. Okay, that is convolution. Because in very different ways we can combine the functions, right? Like, for example, adding two functions. If you add two functions, we obtain another function. That is one way of combining functions, right? And subtracting two functions, also another way of combining functions, right? Or multiplying two functions. This is another way of combining functions, and blah, blah, right? And here we are going to see another special type of combining two functions. All right, here we have a special product because it is different from our usual product. Okay, and this is read as f convolution g. Okay, so this is the definition, how we are defining this special product. So if functions f and g are piecewise continuous on the interval from 0 to the power of infinity, then a special product denoted by f, that special product that start g, is defined by the integral. This f of f special product g, we are defining as integral from 0 to t, f of tau times g of t minus tau d tau. Okay, and also Laplace transform in some way, in different way, we actually define, right, Laplace transform of the function using the integral. Okay, now here we are introducing another special product, and it has very, very useful properties. Soon we will see this, okay, in Laplace transform, and it's called the convolution of f and g. And this thing, so it's called convolution of f and g. You see here the order is important, f and g. But how about convolution of g and f? What is it? And the question comes, f times g here, or f special product here g, is it equal to, actual convolution of f and g is equal to the convolution of g and f? So we will answer this question a bit later. They are equal, but we have to prove. Before we continue, let's say one example. Show that e to the power t convolution here, special product sine of t, that is equal to this. Okay, how they evaluate this? If you just denote here, let's say our function f of t is equal to e to the power t, and here we have g of t is equal to sine of t, right? And using the definition, here we have f, here we have convolution g. Actually, here we have something like this. Both are functions of t, right? So using that definition, that's equal to 0 to t. Here we have f of tau, right, times g of t minus tau. And here we have d tau. That is how we define this, right? Now, if I substitute the given functions from 0 to t, what is f of tau? F function is this, right? F of tau is, instead of t, we have to write here e to the power tau times, here we have g, that is sine of, instead of t, here we have input value here is t minus tau. Here we have d tau. Now these two things we have to integrate with respect to tau. And how can we integrate this? By just using integration by parts method. That is equal to, here we have integral from 0 to t, right, sine t minus tau. I can just bring this inside. Here we have d e to the power tau, right? And here we have u, here we have v. Integration by parts, what we have here, e to the power tau times sine of t minus tau, right? Here we have 0 to t minus integral from 0 to t, and we have to integrate these two things, e to the power tau. Now here I have d sine of t minus tau, right? So I'm going to differentiate this. What is the differential of d d sine of t minus tau. So we can just take this out. If we differentiate with respect to sine, here we will have cosine. Here we will have cosine of t minus tau, right? And here we have d tau. And what is the derivative of t minus tau with respect to tau? Is equal to minus tau, actually minus 1, right? That is minus 1. So with this minus here, actually it becomes plus. Okay, and you know how to differentiate this. Equals, I will continue. First, if you evaluate this, as you see here, if tau equals t, because of this one, right, sine of 0, that's equal to 0. Here we have 0. Minus, how about if tau is equal to 0? If tau is equal to 0, this thing is equal to 0. E to the power 0, that's equal to 0. So here we have sine of t. Plus, and I have to apply integration of by parts once again. I just put this here, right? And what we have here, again, here we have e to the power tau times cosine of t minus tau. And here we have from 0 to t minus integral from 0 to infinity, right? They interchange now. E tau is here. They interchange with each other. Here we have e tau times d. Here we have cosine of t minus tau. All right, as you see here, it's not so short, but well, it's actually very useful because just following fixed rules here. Anyway, so here we have that 0 minus sine of t. How about this one? If is equal to t, right? Here we have 0, cosine of 0 is equal to 1, e to the power t. So here we have plus e to the power t. Minus, how about if it is 0? Here we have 1 cosine of t. So here we have cosine of t. And minus, how about here? Here we have from 0 to positive infinity. Here we have e tau, right? Take to the outside here. Derivative of cosine is sine. Here we have t minus tau. And here we have d tau. And derivative of cosine is actually minus sine of t minus tau, right? And also, if you differentiate this t minus tau, it is also negative 1. Because of that thing, here we have that thing is equal to sine of t minus tau. That means that differential of cosine of t minus tau is equal to sine of t minus tau d tau. All right. So now if you notice here, what we have here. Here we have the original function. If you look at the original function, e to the power tau, sine of t minus tau, e to the power tau, sine of t minus tau, right? So on the left-hand side, I have this. So this thing, if I take to the left-hand side, right, I will have this thing twice. And divide both sides by 2. What we got here? Then we got here integral from 0 to positive infinity, that e to the power tau sine of t minus tau and d tau. That is equal to 1 over 2, because on the left-hand side now I have 2 such functions, right? So I'm just multiplying both sides by half. Now what we got here? Here we have minus sine of t, right? Plus e to the power t minus plus e to the power t minus cosine of t, right? It is exactly the same thing here. Minus sine of t minus cosine of t plus e to the power t. So we have proved that if you are given these 2 functions, e to the power t and sine of t, their convolution is equal to this function, right? As you see here, by simple functions, it's not so short. If you do not practice this, you cannot evaluate this in a short time. That is what we mean by convolution of 2 functions and how do we compute their convolutions. As you see here, we have to evaluate this integral. All right, right after this, let's actually move to convolution theorem. That is actually the key. Thank you very much. That is what we are trying to understand from this chapter. That is the key results of this concept. Okay, it's saying that if function f and g are piecewise continuous on this interval from 0 to positive infinity, Now you should understand every time when we are defining things, actually we are considering on this interval. Why? Because our definition was in this interval, right? Laplace transform was defined on this interval. That's why actually everything is related to Laplace transform. Every time we have to mention this thing. You're not actually talking about the behavior of the function over the whole real number line. Only half of it, right? Starting from 0 to positive infinity. And of exponential order. And of exponential order. And if you remember this, what we mean by this? Actually, by exponential order, right? And piecewise, you understand in calculus you studied a lot. Exponential order, you need to actually remember this inequality. F of t is less than or equal to, or less than, here we have m times e to the power ct, right? For some, actually, t is greater than positive t here. That means that we can have such point after a certain point, right? Let's say this our capital T, right? And after that, if I just cut it into two, above on the right-hand side of this line, right? This function's graph is always below this function, right? That's really important because all the time you will see this, what is it? The ratio of these two things, okay? And here, our f of t, actually, it should be below the graph of this e to the power ct. That is what we mean by exponential order. Anyway, here is saying that Laplace transform of f convolution g is equal to Laplace transform of f of t times Laplace transform of g of t. And what is this? That is equal to capital F of S, right? And how about this thing? That's equal to capital G of S, right? That is very important thing because a lot of times, for example, if I just put here, not the special product, if you just write here, what happens to this? F of t times G of t. Can I use this problem for this? It is not possible. They are not equal, right? It's not equal to Laplace transform of f of t times Laplace transform of g of t. That's why mathematicians were interested. Okay, this property doesn't hold for this. So how should we define this product so that Laplace transform of f of t is equal to the product of Laplace transform of f and g? Okay, that is not so easy, I think, to define such thing. Maybe it took years to reach this conclusion. Okay, so here Laplace transform of f convolution g is equal to Laplace transform of f times Laplace transform of g, and which is equal to f times g. Now from here immediately I can write this equality again. Here we have Laplace inverse or inverse Laplace of f times g, right? That is equal to what? That is equal to this. That is f of t times, right? No. Equals from here, if this thing is equal to this thing, right? If you just take inverses of both sides, what we got here? The inverse Laplace of f times g, that's equal to f convolution g, right? Which is equal to, from 0 to t, here we have f of tau, not t, f of tau times g of t minus tau. That is dt, right? Just to evaluate this, we need to evaluate this integral. Okay. Now that's really also proof is interesting, but it may take a lot of time here. All right, that's why I'm skipping. It is proof. Maybe if I have time, I'll make a video and share with you, or you can just watch and study yourself from YouTube. Now let's see a few properties of convolution. Okay, here, just fourth properties, commutative. So that convolution has commutative property. That means that f convolution g is equal to g convolution f. that is equal to this. Distributive, f convolution g plus h is equal to f convolution g plus f convolution h. Associative here, f convolution g convolution h equals f convolution. First convolute these two functions, and after that convolute f as the result. And f convolution 0, that's equal to 0. Okay, you may try these properties, but here only let's prove one of them. Here, this one, for example. That is actually the most important property here. F convolution g equals g convolution f. Why is this so? Proof. Now, from this integral, I try to obtain this integral, right? Here we are going to use again calculus here from 0 to t. Here we have f of tau times g of t minus tau. Here we have d tau. All right. And the notes, let me just write here. Okay, we don't have much space here. Or, all right, let me just do it here. As I have more space here. So we are going to prove that integral from 0 to t. Let's say, let me just write here, f convolution g. Okay, that is equal to integral from 0 to t. Here we have f of tau, g of t minus tau. Here we have d tau, right? So now we will use substitution method here. What we have here, let me introduce this new thing. Let's say z, okay, equals t minus tau. All right. Now from here, what is dz? Here with respect to tau, that's equal to minus d tau, right? And also looking at this, when actually tau equals 0, right? If tau equals 0, and what is w? If tau equals 0, not w, z, z is equal to, what is it? If tau is equal to 0, z equals t. How about here, if tau, because tau is changing from 0 to t, right? How about if tau is equal to t? If tau is equal to t, right? Here we have t minus t, that's equal to 0, then z should be equal to 0. Making these substitutions, what do we get here? So here we have integral. So here, if I just change this tau into z, if I express everything in terms of z, here, tau, right? Z is changing from t to 0. So here we have t, here we have 0. F. Now from here, what is tau? Tau is t minus z, right? That is t minus z. So that's equal to t minus z times g of, what is t minus tau? T minus tau is z. D, and here we have d tau. What is d tau? Minus dz. So here we have dz. Let me just write minus here. Equals, we know that if I just multiply this integral by -1, we should just interchange the integral, what is it, limits. So I mean, this thing, this minus integral from t to 0 is the same as integral from 0 to t, right? Now it's just times our usual multiplication. Here I have g of z times f of t minus z. That is dz. Now this is just labeling, right? Z and z and z, right? D is changed from 0 to t. As you know from integral, actually this, what is it? This integral from here f of t dt. I can just write anything here, right? It's just an independent variable. How you're labeling your independent variable with t or a or x or y, doesn't matter. It's the same thing exactly as f of z dz, or f of w dw, or f of y dy. Okay, make sure that it does not lead to any confusion here. Yeah, that's so that we are not using a single variable to denote two different things here. So here I can just interchange this, and I can rewrite this as integral from 0 to t. Let me just write it here. G of t, not t, because t is already used here. So instead of z, let's say it is tau. F of t minus tau. Here we have d tau, right? I just relabel this because, again, we are using substitution method, taking z as tau. And what we got here, g of tau, f of t minus tau. That's exactly the same, but instead of f, here we have g. Instead of g, here we have f. That is, what is it? G convolution f. Okay, that means that, what is the result then here? Here we have f convolution g is equal to g convolution f. All right. Okay, that is convolution theorem. Now let's see one example related to this theorem immediately. So transform of a convolution evaluates. Here we have integral, right? Something like this. And immediately we can recognize this. Here, what we have here, if I just take this f of t as e to the power t, right? And g of t as sine of t, right? Now what we have here? Here we have Laplace of f of t convolution g of t. Actually, we don't like this. We can just write it as f convolution g of t. Okay, in a simpler form. Actually, doesn't matter. That is what we have. Very good. Now we have already, actually, we got a formula of theorem that's then this thing is equal to, what is it? Laplace transform of f of t, right? Times Laplace transform of g of t, which is equal to f of s times this thing is g of s, right? Now from here, what is f of s? F of s is equal to Laplace transform of f of t. What is f of t? E to the power t. And we know how to evaluate this. That's equal to, what is it? 1 over s minus 1, right? And how about the second thing? G of s. All right. Here we have g of s is equal to Laplace transform of, what is it? Sine of t, right? And also we're not actually familiar with this. What is it? That's equal to 1 over s squared plus 1 squared. That's equal to 1, right? Then what is this? Then this thing, right? That thing is equal to, I can just write here, is equal to f of s times g of s. F of s is equal to 1 over s minus 1 times 1 over s squared plus 1, or which is equal to 1 over s minus 1 s squared plus 1. Okay. Another thing to, how to say, related to Laplace transform. All right. Guys, are you there?
Yes, sir.
Very good. Inverse form of theorem 7.4.2. We already got it. One more time. The convolution theorem is sometimes useful in finding the inverse Laplace transform of the product of two Laplace transforms. Because we know that Laplace transform of f convolution g, right? That's equal to capital F of s times capital G of s, right? For example, now we are going to consider this example once again. Laplace transform of, for example, sine of kt minus kt times cosine of kt, right? And we have already evaluated this. That is equal to 2k cubed over s squared plus k squared. And here we have squared. Okay. Now in the next section, we'll talk about this and see a few examples. And after that, maybe we'll talk about periodic function. Okay. Guys, now let's have some rest. Okay. A few minutes left. So after 10 minutes, we will continue. See you.